Hi everyone, so this is Unit 3, Lesson 3, Properties of Circles. This is our last lesson in Unit 3, and it's the shortest of the 3 lessons that we're covering, but you'll see how it fits in the same theme. So what we're going to be doing is trying to figure out some properties of circles using the same ideas: slope, midpoint, distance, formula, equations of lines. I only have 2 questions for you here in the lesson, both taken from your textbook. So again, it's a bit tricky because it's not just a matter of following procedures, but using the tools that you're given. So the examples that I'm going to show you use those tools, but they just show you how to use it in a couple of contexts. You're going to have to figure out how to use them in other cases. Okay, so as we said, we're going to be working with circles here, and we only have one new vocabulary term, and that term is chord. So a chord is basically a line that connects 2 points, or I should say maybe a line segment that connects 2 points that are on the circle. So take any 2 points anywhere on the circle, connect them, and that connection that you've produced is a line segment called a chord. Could go through the diameter, but it could be elsewhere on the circle, like here. Okay, so in our first question, what you're going to try to do is verify that the center of this circle, which is here at 0, 0, verify that that 0, 0 center lies on the right bisector of the chord AB. So we have some chord here, AB. We have the coordinates for A, the coordinates of B. We want to show that the perpendicular bisector to this chord goes through 0, 0. Okay, so how can we do that? Well, if we have the equation of the perpendicular bisector, then we can see if it goes through 0, 0. Right? We can plug in 0, 0 and see if that's actually on that line. So can we get the equation of the perpendicular bisector? Well, one way to get the equation of a line is to find the slope and find a point. And you'll see that we can do that because the bisector goes through the middle of AB. So a point on the bisector will be the midpoint of A and B. In addition, you can find the slope of A and B. And since this is a perpendicular bisector, the slope of the bisector will be the negative reciprocal of the slope of AB. So we just got to find the slope of AB and its midpoint, and then we're on our way. Okay, so the midpoint of AB, that's the midpoint formula that we've been using. So you have your x's, you have your y's, sub them in, and you end up getting 3, -1 as your midpoint, which looks about right. Okay, so there's 3 and there's -1. So again, if you do this stuff on a graph, it helps you kind of orient yourself, understand the problem, and see if your solution is looking reasonable. And this one is. Okay, slope of the line. So that's m equals y2 minus y1 over x2 minus x1. And again, we have our y values here, our x values there. Just plug them into the formula. Watch your signs, right? 2 minus -1, 2 minus -4 is the same as 2 plus 4. So that's going to give you 6. And so you're able to calculate the slope of AB. Alright, so remember, it's not the slope of AB that we want, it's the slope of this line, and that's the negative reciprocal. So the negative reciprocal of 3 over 1 is -1 over 3. So we now have the slope of AB, we have the slope of the bisector, right bisector, and we have a point on the right bisector. That's enough to now get the equation. Because if we have y equals mx plus b, we can sub in the slope, we can sub in an x from the midpoint, y from the midpoint, and solve for b, which is 0. So now we have m, we have b, so y equals mx plus b, y equals -1/3 x plus 0, or just y equals -1/3 x. So that's the equation of our right bisector here. So is the point 0, 0 actually on this right bisector? Let's find out. If we put 0 in for x, -1/3 times 0 gives you 0. So a 0 value for x gives you a 0 value for y. So yes, 0, 0 is actually on this right bisector. So we can conclude that the center of the circle is at 0, 0, lies on the bisector of chord, this should say AB. Okay, so is that a coincidence? It turns out no. So if you take the right bisector of any chord on a circle, you are going to find a line that passes through the middle. So the right bisector of any chord will always pass through the middle of the circle. That's the chord bisector theorem. So let's quickly look at why that might be true. Okay, so just going to make this a little smaller here. The first thing to know here, this is a little confusing, but there's sort of just 2 main points here. So the first thing to know is the center of the circle is equally distant from any point on the circle. What does that mean? That means if you're at the center of the circle, any point A, B, C, D, any point you want is going to be the same distance from the middle of the circle. And that distance is just the radius, right? That's how you define a circle. A circle is a point, and then you go a radius distance away from that circle. Every point that distance away will form the circle. So a circle is really just a collection of points that are all a radius's distance from the center. Okay, so the center of any circle is equally distant from any point on the circle. So if we can show that any point that is equally distant from A and B is on this line, then the center of the circle must be on this line. Because it turns out that's what a perpendicular bisector is. A perpendicular bisector gives you all of the points that are equally distant from A and B. So this point here in the middle, we can tell that's the midpoint. We already know that that's equally distant from A and B. But that's true of any point on the right bisector. So if I was to, say, draw a line here, let's draw a line. So this point here, whatever this might be, this might actually be the center of the circle. What you can see here is we've created two right triangles. So yeah, that's not very good. But in any case, we know that this is a perpendicular bisector, so both of these are right angles. So we've created two right triangles. But look, we know that the black line here and the black line there are the same length because this is a midpoint. So these two must be the same. In addition, the red or pink side is shared between both triangles. So this length must be the same for both triangles. So if this is A and this is B, we know that for a right triangle, A squared plus B squared equals C squared. So A squared plus B squared, the A here and the B here is the same as the A here and the B there. So if A squared plus B squared equals C squared for here and for here, C squared is the same for both of these hypotenuses in green, so C must be the same for both of them. In other words, these hypotenuses are the same. They're the same length. So this point here is equally as far away from B as it is from A. And you can make a right triangle at any point you want on that pink line, and that will be true, right? That point will be equally as far away from A and equally as far away from B. So if this line contains all points that are equally as far away from A as it does from B, it must contain the center, because the center is a point that is equally distant from A and equally distant from B. So this line, in other words, contains a lot of points that are equally distant from A and B, but one of those points must be the center, because the center has that property, right? The center of a circle is equally distant from any 2 points on a circle. Okay, so that's the chord bisector theorem. Let's go back. Points on a circle. So show that the points P 9, -3, Q 8, -6, R -1, 5 lie on a circle with a center of 4, 1. So remember what we just said on paint there. We just said that the center of a circle is equally distant from any point on the edge of the circle. So all of these points will be equally distant from C if we have a circle. So if I can show that all of these points are equally distant from C, then they will all be points that are on a circle with a center at 4, 1. Right? Now, what I want you to just quickly think about here, though, is you can't define this circle by x squared plus y squared equals r squared, because its center is not 0, 0. But you can do this question, right? You can see, are these points all equally distant from 4, 1? Because we have a formula to do that, right? We have the distance formula. So I'm going to check if PC, QC, and RC are all equal. If they are, then P, Q, and R all lie on some circle with 4, 1 as the center, and that distance that we're calculating here will actually be the radius of that circle. Okay, so all we got to do is use our distance formula and plug in our x's and our y's for PC, QC, and RC and see if they are all actually the same length, if they're all the same distance away from our center of C. And it turns out if you do that, they are, right? The distance of CP, CQ, and CR are all root 41. So it turns out that you have a circle with a center at 4, 1 with a radius of root 41. All of these points are on that circle. Okay? So that's what this would look like. So if you've got P, Q, and R, you have the middle here, they are all root 41 away. They're all one radius away from the center. Trickier question. Does any other circle pass through the points P, Q, and R? So it's tricky to first of all understand what this question is asking. So what it's saying is, we know that we have a circle with a center of 4, 1 that passes through all these points. In other words, if you draw the circle, like we have here, all of those points P, Q, and R will be on the edge or the circumference of the circle. But we can ask, is it possible to draw another circle somehow that also includes all three of these points? Or is this the only one? Well, let's find out. So what we're going to do is we're going to use what we understand about right bisectors to show if we can do this or not. So this is a little tricky, as I said, to understand, but let's give it a go. So if you have these points R, Q, and P, you can draw chords between them. So you can draw a chord between R and Q and a chord between Q and P. And each of these chords is going to have a right bisector, right? So R and Q will have a right bisector, and Q and P will have a right bisector. Well, what does the chord bisector theorem say? It says that the center of the circle must lie on the right bisector to a chord. So this right bisector here in pink goes through the middle of the circle. So all this stuff here is really just telling you is, draw two chords, and then draw their bisectors. And you don't even actually have to calculate them, right? You can just make this argument, the fact that you can do this. So if you have a bisector that goes through R and Q, you have one line. If you have a bisector that goes through Q and P, you have another line. And you could prove this geometrically, but even just looking at this, you can see that these two lines, your two bisectors, they're not parallel very clearly, and they're not the same line. So if you have two lines that are not parallel and are not the same line, how many places will they actually intersect? Well, hopefully you know from the first unit that if you have the same line, you have infinite solutions. If you have two parallel lines, you have no solutions, no points of intersection. But in any other case, your lines will only intersect at one point. So, what does that mean? Well, we know that the center of the circle must lie on the bisector from RQ by the chord bisector theorem. So this light blue line going up and down, the center of the circle must lie on this line. But we have another chord here with a bisector. The center of the circle must also lie on this line. So you have a center of a circle that must be on both this line and this line. There's only one point where that's going to be true. There's only one point that's on both of these lines, and the center must be on both of these lines. Therefore, the center must be on this point. There is no other point that it can be at. So therefore, the circle with center 4, 1 and a radius of root 41, right, which we determined up here, is the only circle that passes through the points P, Q, and R. So in other words, if you have 3 points, you're only going to have one circle with one center that can go through all 3 of those points at the same time. Okay, that's the last example that we're going to cover here. So hopefully that gives you enough to work on your assignments, but please do some practice questions ahead of time so that you are prepared. Good luck, and that's the end of this one.